Hey folks, welcome back. In this video we're going to go over detecting signals from space. So let's get started. So we'll be looking at how to detect signals from space, including the use of telescopes. And it starts by saying astronomers detect electromagnetic radiation from space. You should remember the order of the electromagnetic spectrum from the waves topic. So you can either remember it in terms of decreasing wavelength starting at radio waves and decreasing in wavelength down to gamma rays, or you could remember it starting from gamma rays and increasing in wavelength up to radio waves. Or you can think about it in terms of frequency, so going from radio waves down to gamma rays we have increasing frequency and energy. And remember the first two types of EM radiation here are often grouped together into the same category. So we'll get radio, TV, microwaves, infrared, visible light, ultraviolet, X-rays and gamma rays. And you might have your own way of remembering this, such as your own mnemonic or the electromagnetic spectrum song. But in the waves topic I gave you mine, which was running through my bowl and vibrant underwear excites grannies. And depending on where you're from, you could change the M to be just the name of a place beginning with M that's near you. So as we go from radio waves down to gamma rays, the energy of the electromagnetic radiation increases, and that means it gets more dangerous, remember. It then says different detectors are needed to pick up different types of signals, i.e. different wavelengths or frequencies. So you would have looked at detectors for the different types of electromagnetic radiation in the waves topic, but here's a summary giving you just one detector for each. So for radio or TV waves we have an aerial, microwaves we also have an aerial, infrared we could have a photodiode, visible light we could have the retina of the eye, and just make sure you're stating the word retina rather than the word eye if you're asked about this in an exam question. For ultraviolet we've got fluorescent material, for X-rays we've got photographic film, and lastly for gamma rays we've got a Geiger-Müller tube. So it's worth remembering one detector for each of these types of radiation. And it's also worth pointing out that each of these types of electromagnetic radiation have their own telescopes to detect them. And I'll just show you a quick simulation to help you understand this. So if you look here, we've got the full electromagnetic spectrum going from radio waves on the left to gamma rays on the right. And we're saying there are different telescopes to correspond to the different types of electromagnetic radiation. So if we click on radio, first of all, you'll see the radio telescope picture there. And it says radio telescopes are large. They consist of very large dishes which focus the radiation on a detector, and we'll talk a bit more about these shortly. For microwaves we have microwave telescopes which look like this, and it says they do not need to be as large as radio telescopes. Microwave radiation is the cosmic microwave background radiation that fills the universe. Moving on to infrared, we have infrared telescopes which look like this, and it says that many infrared wavelengths are absorbed by the atmosphere, so infrared telescopes need to be on high mountains or even in space. Moving on, for visible light we have optical telescopes, and it says that visible light makes up only a very small part of the spectrum. Visible light is not blocked by the atmosphere, but clouds and dust can scatter light, so most powerful telescopes are built in high and dry places. Then for ultraviolet or UV we have ultraviolet telescopes which look like this, and it says UV radiation is absorbed by the ozone in the upper atmosphere, so ultraviolet telescopes must be placed in space. We then have X-rays with the X-ray telescopes, and it says the X-rays are absorbed by the ozone in the upper atmosphere, so X-ray telescopes must also be placed in space. And lastly we have gamma rays, so we need gamma ray telescopes to detect them, and it says only the shortest wavelength gamma rays reach the surface of the Earth, so many gamma telescopes are in space. Going back to the notes now, we're going to look at telescopes in a bit more detail, and in particular we're going to look at optical telescopes and radio telescopes. So it firstly says when we look at the sky, our eyes receive light from astronomical objects. However, the lenses in our eyes are so small that we cannot see these distant objects in great detail. If we wish to get a better view, we can collect more light by using a telescope with a large objective lens or mirror. So optical telescopes are based around the idea of collecting light. The more light you collect, the further into the distance you're able to see and the more detail you're able to see. And it says, for example, the Hubble Space Telescope has been put in orbit around the Earth and produces stunningly clear images because the light does not have to pass through the atmosphere, which would distort it. So Earth's atmosphere is a problem for optical telescopes placed on Earth, but if you place telescopes in space, then you don't need to worry about the Earth's atmosphere getting in the way. It then goes on to talk about radio telescopes here, and it says radio telescopes have large curved dishes which can pick up weak radio waves from space by focusing the waves on the receiver. All the weak radio waves cross over at this point and combine so that a strong signal is picked up by the detector. And the picture here shows an array of radio telescopes in a field, which is often where you would find them alongside other radio telescopes. And we're saying that weak radio waves coming in from space are going to hit off this large curved dish, and it's going to reflect the weak radio waves from each point hitting the dish to this receiver here. and it's at this point at the receiver that all of these weak radio waves will combine or overlap to form a strong radio signal. And to help you visualize this, I'll just show you a quick simulation. So here we have these straight lines called rays, and let's say these are our weak radio waves coming in from space. And we've also got a detector here which is hooked up to this box to tell us the signal strength. And right now we've got no reflector. However, if we put a small reflector in place, then notice how some of the weak radio waves are going to reflect off the curved dish, and they're going to all meet or overlap at the point where the detector is. And you'll notice that our signal strength has gone up a wee bit. We're getting a non-zero signal this time because we are getting some overlapping of the weak radio waves to form a slightly stronger radio signal. However, if we used an even bigger curved dish or reflector, then notice how our signal strength goes up, and that's because we're getting a lot more weak radio waves coming in and reflecting off the curved dish to then overlap at the detector. So because of that increased number of weak radio waves overlapping, that's caused a greater signal strength. And being able to detect strong radio signals is important because if they're reaching the Earth from stars or galaxies that are very far away from us, then it's useful to have as strong a radio signal as possible to work out different properties of these stars and galaxies. That's all for this video, folks. Thanks for watching. If you made it to the end, I really appreciate it. Make sure to give the video a thumbs up, subscribe to the channel, and I'll see you in the next one. Take care.